All right, this is Jack Jackson. We're going to talk about a really cool class of quadrilaterals today, and that's parallelograms. So by definition, a quadrilateral is a parallelogram if and only if it has two pair of parallel sides. So by our inclusive definition of a trapezoid is a quadrilateral with at least one pair of parallel sides. A parallelogram is automatically a trapezoid, so of course it has all of the properties of a trapezoid. Of course, no parallelograms or any other types of trapezoids exist in spherical geometry. Because of the existence of multiple parallel lines to a line through a point not on the line in hyperbolic geometry, trapezoids and parallelograms in hyperbolic geometry turn out to be a much larger class of objects than they are in Euclidean geometry, and they do not have all the cool properties that parallelograms have in Euclidean geometry. But in Euclidean geometry, they do have a lot of pretty cool geometry, uh, geometric properties. We're going to talk about those a little bit in this video today. In Euclidean geometry, if we're given any three nonlinear points A, B, and C, then they completely determine a parallelogram A, D, B, C, D. Since there's exactly one line to parallel to AB through line segment AB through C, and also exactly one line parallel to BC through A, and their one and only intersection point must be the remaining vertex D. This is a way you can construct a parallelogram by the definition in GeoGebra or Geometry Sketchpad. The situation in hyperbolic geometry is different. In hyperbolic geometry, there are infinitely many lines parallel to AB, line AB through or line segment AB through C, and also infinitely many lines parallel to BC through A. Choosing the intersection of any pair of these produces one of the infinitely many possible values for the remaining vertex D. Parallelograms in hyperbolic geometry form a much more general class of figures and have fewer forced properties than the class of parallelograms in Euclidean geometry. So here's a task for you in Euclidean geometry. And try to do this before you proceed. Construct a general parallelogram in Euclidean geometry using the standard parallel line tools in GeoGebra. Measure all the interior angles. Make a conjecture about consecutive angles. Test your conjecture and then prove it. No additional constructions, for example a diagonal, are necessary. Now, next measure the sides. Make a conjecture about opposite sides. We know they're parallel. Is there anything else you can say about them? Test out your conjecture. Don't get to a proof just yet. Construct one of the diagonals. Actually, doesn't matter either one. Or does it work? Try to see. Make a conjecture about the two triangles that are formed. Prove, test out your conjecture, and improve it. Does it work if you switch to the other diagonal? Hide the first diagonal, draw the other one. Do you get the same conclusion? So prove that, and then use that proof to prove your conjecture in part 3. Now show both diagonals simultaneously and let X be their intersection, and they will intersect. Make a conjecture about certain parts of the 4 smaller triangles that are formed. Test out your conjecture and then prove it. What does that say about the 2 diagonals? In other words, specifically, where is X on each diagonal? And use your proposition from the previous part to help prove this. Okay, so see if you can do this task on your own. This is a great discovery task. It's not hard to construct in GeoGebra, and you can do this and find out a lot of cool things about parallelograms. Okay, so do that yourself and come back in the next video when you finish that task.